So today we're going to discuss half-life. We've already talked about how radioactive elements decay and turn into something more stable. Today we're going to talk about how long does that process occur for. So the question we're going to be trying to answer is how long does it take for a sample of radioactive material to decay? And there's really no simple answer to this question. So to understand radioactive decay and how the process occurs and how long it takes allows scientists to do a lot of different things. So one, it allows them to predict how long an isotope that is radioactive used in medical diagnosis or treatment will remain in the human body. So here you can see a sample on the far right, on the top here, of some radioactive medicine that's going to be administered to a patient. So we can use radioactive dating and half-life to help determine how long that isotope is going to remain in the human body. Another thing we can determine by understanding how materials decay is how long it will take hazardous waste to be stored. So here's a picture, the second picture here is a storage of radioactive material. So how long do we have to store that? So if we understand radioactive decay, it allows us to predict how long we have to store waste from nuclear reactors. And the last thing it allows scientists to do is to estimate the age of ancient organisms or civilizations or rocks. So we can radioactively date materials. So that bottom picture here is showing you like a granite rock will contain uranium. And as it decays, it turns into the more stable form lead. So we can estimate and approximate how long that time period will be if we understand radioactive decay. So in order to understand how long it takes, we're going to talk about something called half-life. So in 1904, Ernest Rutherford proposed this first concept of half-life to describe the random process of radioactive decay. And so we define half-life as the time it takes for 1/2 of the total atoms in the original sample to decay. Here you can see examples of different half-lives. So hydrogen-3, the isotope of hydrogen, takes 12.3 years to decay to half of its radioactive material. So at that time, after 12.3 years, half the material is radioactive, half the material are not. Carbon-14 takes quite a long time, so 5,730 years. Phosphorus only takes a couple days, so 14.3 days. Potassium takes a very long time, so 1.2 times 10 to the 9th years. And radium takes about 3.28 days. So the time it takes for half of the total atoms originally present in the sample to decay is the half-life. And so we can use the property of half-life to do a lot of different things. And the most common usage is carbon dating or radioactive dating. And so we look at carbon-14, which is a radioactive element. And so all living matter contains carbon, and therefore a small amount of that carbon in our bodies is carbon-14. And so carbon-14 atoms decay in living matter, and they're constantly being replaced into new carbon atoms. So as long as we're alive, we keep replacing that decaying carbon-14. However, once we die, no new carbon atoms are taken in by our organism. And so we can measure how much of that carbon-14 is left in the organism's body after we discover it or find it. So we call this process carbon dating. And so it's been used a lot with fossils and rocks and minerals and stuff like that we found. So one of those example cases, it was in 1991, a frozen human body was found in the Alps. And it was originally thought it was a murder that had occurred, but then they found out that the body was actually a Neolithic man. And so he got the name of the Iceman because he was found in a glacier. So scientists were able to measure the rate at which carbon-14 was radioactively decaying in his body. You could see a picture there of the body that they had found. And they observed some of the emissions as well from the belongings that were found with his body. And they found that it was slightly more than 50%, the rate was, left in the organism today. And so we know how carbon-14 decays, and you can look at the graph up here. And about halfway, so just above 50%, if we look at our scale here, so just above 50, so let's say 55% of the carbon-14 atoms remained, and that will tell us how old the organism was. And so it was estimated, therefore, that the Iceman died about 5,300 years ago, because they could measure how much of that carbon-14 had remained. And so here's just an example of what half-life is. So if these are the atoms of our radioactive material, we have 8 of them. If we go through one half-life cycle, okay, we're going to remove 8 of those atoms. And then if we go through another half-life, we would have 2. If we go through another half-life, we had 1. Another half-life, we would have a half. Okay, so we're going to keep cutting that in half each time, thus the name half-life. And so if we were to plot that, we're always going to get this exponential curve. So it's going to kind of go towards 0, but it's actually never going to reach 0. So it's just going to keep cutting it in half and half and half again. But it gets to such a small value that we can't even measure it anymore. So let's try a couple of example problems. So if we have 100 grams of radioactive carbon-14, the half-life of C14 is 5,730 years. How many grams are left after one half-life? So if we're starting with 100 grams, to get to our first half-life, we're going to cut our material in half. So we're going to take our 100 grams, we're going to divide it by 2, and we get 50 grams that remain. So after one half-life, 50 grams of our substance would remain. Okay, so how many grams are left after 2 half-lives? So we're going to take our 50 grams that remained after 1, and we're going to cut it in half again. And so we would have 25 grams of carbon-14 left after 1 half-life, after 2 half-lives. Okay, let's try another one. So manganese 56 is a beta emitter, so it's going to give off that beta particle with a half-life of 2.6 hours. What is the mass in a 1 milligram sample of that isotope at the end of 10.4 hours? So on a lot of these problems, I like to draw out a table. So the number of half-lives in my first column, I'm always going to start with 0 times, 0 half-lives. Then my second column, I'm going to put time. And then my last column, I'm going to put amount of my sample that I have. So at time 0, when 0 half-lives have gone by, I'm starting with a 1 milligram sample. So after 1 half-life, so 1 half-life is 2.6 hours. I'm going to cut my sample in half. So I have 0.5 milligrams left. Now I need to go until my time says 10.4 hours. So 2 half-lives. So I'm going to add another 2.6. So 2.6 plus 2.6. And we get 5.2 hours. And I'm going to cut my sample in half. Half-life, cut it in half. So 0.25 milligrams. I'm still not at the right time, so I got to get to 10.4. So I'm going to go to another half-life. So 3 half-lives. I'm going to add another 2.6. So I get 7.8 hours. I'm going to cut my sample in half. So 0.25 divided by 2 gets me 0.125 milligrams. Still not at the right time, so I have to go to another half-life. So after 4 half-lives have gone by, I add another 2.6, and I get to my 10.4. And then I'm going to cut my sample in half. So 0.125 divided by 2, so I get 0.0625 milligrams. And so my answer, my question asks for how much mass is remaining at the end of 10.4 hours. So my answer would be 0.0625 milligrams remaining after 10.4 hours. So it kind of helps to kind of organize your answer by creating this table. Let's try another example. So carbon-14 emits beta radiation and decays with a half-life of 5,730 years. Assume you start with a mass of 2 grams. How long is 3 half-lives, and how much sample will remain after 3 half-lives? So again, I'm going to draw out my table. So number of half-lives. So I need to get to 3 half-lives for this example. How much time has gone by is my second column, so I'm always going to start with time 0. And then my amount of my sample is the last column. So I'm starting with 2 grams. And I need to go to how long is 3 half-lives, how much remain after 3. So after 1 half-life has gone by, 5,730 years have expired. And my sample is cut in half, 1 gram. So I'm now to get my next half-life, 5,730 added to the one before. So I get 11,460 years, and half my sample, 0.5 grams. Now one more, so add 5,730 to the one before, and I get 17,190 years, and cut my sample in half, 0.25 grams. So my first question, how long? So it'd be 17,190 years. And how much of my sample? 0.25 grams. So the table is really helpful when you're doing these problems. But if you don't need to use the table, you don't have to use it. Okay, so let's try one more problem together. So a mass of cobalt-60 in a sample is found to decrease from 0.8 to 0.2 in a period of 10.5 years. What is the half-life? So now we don't know the time that we're increasing each time. We don't know the half-life. So let's try this problem. So again, I'm going to build my table. So the number of half-lives, my time, and my amount of sample. So I'm always going to start with half-life of 0, time of 0, and I start with 0.8. And now I need to get to 0.2. So if 1 half-life goes by, I don't know the time, so I'm going to leave that blank, but I would have 0.4 grams. Okay. 2 half-lives, I don't know the time yet, but we're going to cut it in half, so I get to 0.2. So now when I'm at 0.2 grams, I know my time is 10.5 years. So to get my half-life, or how much I'm counting by each time, I'm going to take 10.5 divided by the number of half-lives I'm on. So I'm on number 2. So if I take 10.5 divided by 2, I get a half-life of 5.25 years. So I know my half-life goes up by 5.25 years each time. Now if I was on half-life, let's say number 3, then I would divide this by 3 to get how much I'm counting by each time. Okay, so I think we'll stop there. Give this more of a try on your practice worksheet for today.